Yes, excellent. So thanks for having me. I'm Leila Hieta. I work at Finnish Meteorological Institute. I used to work as an operational weather forecaster for about 10 years. And about 3 to 4 years ago, I started to work in research applications group as a developer and project manager. And the main thing that I do is to develop post-processing methods to improve the quality of our operational weather forecasts. So I mainly do work with the data that you can see in your mobile apps and in our web page. So when you see some weather forecast there, so I do work with that data and I try to make the forecasts better and also provide better data for our weather forecasters. So that's a little bit about me. So I know that, was it a week ago or so, that my colleague Roope Tervo was here to tell you about artificial intelligence used in weather forecasting. So some of you may have seen this slide already, but I tell you a little bit about FMI. So the institute has about 700 employees. It is a research institute, but it's also providing operational weather services. So about half of the employees are somehow doing work with the operational weather services. Our main focus, of course, is to provide good weather observations and forecasts for Finland, but we also provide global weather forecasts. And by the way, I'm unable to see if there will be some written questions in there, so please just interrupt me, or maybe Alex, you can ask me the questions. Yes. Because
Leila, there was one question. Could you make the slides full screen, please?
Okay, yeah, I tried that one, but it didn't work. No. Yeah, no, sorry about that one. Okay, so I give you first a very short introduction about how numerical weather prediction works, and the second part of my presentation will be about my project work. I participated in this excellent machine learning course last spring and did a project work about the temperature post-processing, and that the second part of my presentation will be about my Jupyter notebook and going through the results and what I did in my project work. But first, a little bit about the numerical weather prediction. So it's physical modeling of the atmosphere. Those are calculated to our regular grids. Of course, they have a certain horizontal and vertical resolution. The horizontal resolution quite normally ranges from 1 kilometer to about 10 kilometers. Can be even coarser models, depending if they are global or if they are regional models. Regional models, of course, can be higher in resolution. But the limitation is that the models are very complex and they normally need supercomputers to calculate these weather forecasts. So, of course, if we are calculating just regional models, then we can use a higher resolutions in our models. So to be able to calculate the weather forecasts, we need to know what is the initial state, the observations that we start from. So the weather forecasters, prediction models, they need to have a very good quality weather observations. And we use atmospheric soundings. Weather satellites are very important. Weather radars and, of course, ground observations are assimilated to the weather models. But of course, there are large areas where we don't have much observations, for example, the sea areas. So then we mainly are using weather satellites for those areas. So, of course, we don't have an perfect information from all the locations from the Earth, that's what's happening. So the information is not perfect. Models are very difficult. They are difficult to produce, so they are developed in international consortiums, and this international collaboration that we have in Europe is called European Centre for Medium Range Weather Forecasts, and they have a very good quality global model called ECMWF. Most of you maybe have heard about that one. But there are a lot of these models that are produced, and there is a lot of also collaboration between different national weather services who are sharing the information, for example. There are different kind of weather forecasts. There are deterministic forecasts, which are the most, I guess, well-known forecasts. So it's just one model and gives you just one value of temperature for tomorrow, for example. And there are ensemble forecasts. I will tell a little bit more about them later. And then there are climate models or seasonal models. They are normally calculated with similar model, but they are much more simple because they're not trying to forecast you an exact temperature for a day, but they are giving average values instead. So what causes then uncertainties in the numerical weather prediction? First, I have to say that the models nowadays, they are really good. Of course, some things are more difficult to forecast compared to some other, and of course, also some areas in the world are easier to forecast compared to some other. For example, Finland, we happen to be in an area where two different kind of air masses mix together, which means that we have a lot of low pressure systems coming and going, and those are really difficult to forecast. The weather can change quite quickly, and even small changes in the root of the low level systems of these low pressure systems can cause a big difference in the weather. But luckily our weather in Finland, it's quite safe, so we don't have hurricanes, for example. But of course the uncertainties in numerical weather prediction are caused by, we don't know the perfect state of the initial state, so we don't have observations from all around the world.
Leila, one quick question. Are you
Yes.
still showing slide 3, or is the screen frozen?
It should say like forecast uncertainties in numerical prediction, weather prediction.
Yeah, we still see numerical weather prediction slide.
Oh no, why is it doing so? How can I fix that one?
Maybe the presenting doesn't work when you made the full screen.
Okay.
Yeah, now we see forecast uncertainties.
Okay, that's strange. I don't know if I can fix that one.
Yeah, then let's stick with this not full screen and just
Yeah.
normal
Well,
view.
Yeah, sorry about that one.
No worries.
Okay.
Thank you.
So, okay, there are uncertainties in the initial state. Then, of course, some of the complex physical processes, they need to be simplified in the models. That causes uncertainties. Then some phenomena are not well modeled because of the coarse model resolution, for example, convection and the topography. And of course, atmosphere is a chaotic system, so even very small errors in the initial state can lead to large errors in the forecast. So a little bit more about the model resolution. So of course, the smaller the resolution, the better we can actually model what's going on there. So there is a example in the picture from northern Finland with different resolutions. So if we go to a coarser resolution, cannot know what's happening, for example, in the topography there below. So the resolution defines how well the model can see, for example, mountains, valleys, lakes, and shorelines. And most of the areas are the kind of areas that most of the people also live in. People live in valleys, they live near shoreline. So those are quite difficult places to forecast. And also the topography may not be well presented in the models. So if we are seeing, like, this is example of one observation station, this Kilpisjärvi. Kirkonkylä observation station is at the elevation of 480 meters. But for example, in the weather model, that's horizontal resolution is 9 kilometers. The elevation for the same location is almost 700 meters. So there is almost 200 meters difference in the elevation, what the model sees and what's the reality. So of course it's a big difference when we are thinking about forecasting the temperature, for example, if it's 200 meters higher. And if there is a mountainous areas, even more mountains that we have in Finland, so of course it gets even more difficult. And there is a very simple picture trying to represent what the model sees, so what are the model grids compared to the reality there, if we have some changes in the topography. So the model is unable to see what's actually happening in there. Whereas we are normally interested to a very local weather, but the model is actually what it is forecasting. It's forecasting to these grids instead. So a little bit more about the ensemble forecasting. So what people are most common about is the deterministic forecast. So we take the best estimate of the observations and calculate the best model that we have, and we end up with one solution for our forecast. And that's in the picture represented with the red curve in here. But then, since we know that we have uncertainties in the initial state, instead of calculating just one model, we change a little bit the observation information within the error thresholds and calculate the model multiple times, and then we end up with having an ensemble. And the number of the models can be like 10 from 10 members to around 50 members. Of course, it takes more time, computer resources to calculate all these models. So the same model is run multiple times, and we can either change the initial conditions or we can slightly modify the weather model that we are using. And the ensemble forecast then give you an indication of the range of possible future states of the atmosphere instead of giving just one value for you. So I guess the normal weather user don't really use much about the probability information, instead maybe of the probability of precipitation, but then it makes more sense if we think about, for example, hurricane forecasting. So then we don't want to rely our decisions just based on one outcome of the model. We want to know what's the probability that where the hurricane will hit, where should we go, out of the way to keep people safe. So then it makes more sense to use the ensemble forecasts. Okay, that was about the very basic information about weather forecasting. Now I tell you a little bit about the post-processing methods that we are currently using at FMI to improve the quality of our forecasts. So one of the methods is called Model Output Statistics, MOS, and it's a statistical post-processing method, and it's already developed in US in 1972. So it's not very, very new method, but it's been very good in performance, and it's been used, in decades already. And it's a multiple linear regression technique to predict the near surface quantities using archive of model variables and observations. So we implemented this at FMI around 5 years ago. I know that there's been some kind of MOS already before used at FMI, but not operationally. So we launched the development, and it's now operational around 5 years ago at FMI. So we are using observation model pairs, and they are formed for each individual station, forecast length, analysis hour, and season. And it's working all year round, and it provides 10-day MOS forecasting system for European domain. So with all these stations and forecast length, we end up with quite many statistical models. So almost 1.5 million statistical models.
Leila, one question. So could we consider a data point here as a pair of a particular observation station and a model,
yes.
A statistical model?
Yeah. Yes. This is trained against observation stations. So I have in this next slide is an image of all the observation points used. So we train our own model for each of these station points, and also for every forecast length, analysis time, and season. So we end up having a lot of statistical models in there. But model is trained for all of these points in here are used in the MOS. But since almost all of our production at FMI is provided in grid, so we have to grid this information. And here's just an example of the most product when it's gridded. So we have been testing different kind of gridding methods. And of course, the gridding always decreases the quality of the data, but we still have to do it because people have to be able to have forecasts for every location, not just the observation points, of course. And then another example is the calibration of ensemble forecasts at FMI. So there are two different kind of methods that we are using. One is a linear regression method, quite similar than the MOS. And another one is quite new one. It's done in collaboration, in this Nordic collaboration called METCube. And we're using now deep neural network to make this calibration. So these ensemble forecasts, they are quite often overconfident in the beginning of the forecast. So in this picture, I have one model forecast and the fractals of the ensemble. You cannot really see it very well, but the solid lines are representing the raw model ensemble, and then the dotted lines are representing the calibrated one. So we want to increase the spread of the ensemble model to actually give you an estimate of the true forecast error that is there, because we know that the model is too overconfident here in the beginning of the forecast. So that's something that we want to achieve with the calibration. Another thing is that we want to take out the bias that we have in the ensemble mean. So these are the two things that we are trying to fix in the ensemble forecasts. And they are produced now for temperature, wind speed, and precipitation amount. And as I said, this is just almost operational, this deep neural network. I haven't really seen any results yet from that one, but we're getting there. So where could machine learning, where is it used and where could it be used? So actually in weather forecasting, there is a lot of machine learning and artificial intelligence already included. So one thing is making observations. So making observations from pictures, for example. I know that the cloud cover has been done, estimates have been done, or observations from pictures, and also the visibility observations. Then quality check text that could be used also in those. And then there are weather predictions that are solely using neural networks without any physical model in there. So just using the observations. Then there is post-processing that I just told you about. Then impact analysis. So nowadays, weather forecasters are not just providing information about just numbers, giving you like information that there will be gusts of 21 meters per second tomorrow, but they are more giving out the information that what will it cause, what will be the impact, will there be trees falling, or what will happen when we have that kind of high wind gusts in there. And then machine learning could and is used for correcting crowdsourced observations. So we are getting more and more data from general public and different kind of, from mobile phones, for example. It's possible to collect data, but quite often the data is not very good in quality. So what we are mainly doing nowadays is that we do quality checks and we take out all the bad observations, but what we have to do in the near future is to correct those crowdsourced observations and do some sort of bias correction. I know that there are already methods to do that kind of thing.
Do you have already apps for crowd sensing, or what is the most important application now for crowd sensing, if there is already?
I don't think I understand your question. What was it about? So what is the most
important application now where you at FMI, instead of weather stations, use input from users, from smartphone users? For example, I regularly use this Google weather forecast, and since recently they ask for clicking, does it rain now? Yes or no. So they ask me to do crowd sensing.
So we have the application that you can send your weather observations and the pictures to FMI. So we are now collecting the data,
Yeah.
but we haven't, I don't know that we have really used that data yet.
Okay.
What we are now working with is the NetAtmo data, though. So there are these NetAtmo observation stations that people can buy. It costs like 100 euros about, and the company is selling the data, and FMI has been now doing quality control for the data, and the data now goes to the forecasters to use. But we are not using it yet, for example, in post-processing, since we have to check that the quality is really, really good. So the quality control is working. So some of the challenges there are in operational post-processing. So the methods have to be robust and fast to produce, and they have to work 24/7. And quality control is really important. We don't want to have some unphysical values going out to our customers. Training the model can take time. For example, to MOS, as I said, we have quite many of those statistical models that we have to train. It takes a lot of time, but in the end, the production of the forecast is fast, so it doesn't matter. So the methods don't always have to be super simple. We can use more sophisticated ones just if the forecast production is fast enough. When you start to develop something new, you have to think about the whole production chain. So where will the model be run? Do we have that kind of operational environment that we can actually produce it and so on? So it takes a lot of time. And not all the data is stored or easily available. So weather forecasts, they produce a lot of data all the time. As you can see from the picture, the data amounts are growing all the time. We cannot store all of the information, or then the data may be stored in a place that it takes time to retrieve the data. So it's not always, there is not always enough data available to produce a statistical model. And for example, one example of this model data retrieval, we are now currently upgrading or regenerating the MOS archive that we use, and we are downloading the model data from ECMWF Mars archive, and the estimate for the data retrieval is that it will be ready next summer. So it will take almost a year to get to download all the data from the ECMWF archive. So it can take a really long time. And of course, like in all places, we have a limited human resources in development. So even though one might have many ideas, there is just some of those that you can actually do. But as Alex already said, there is a lot of data available at FMI's open data. So we opened our data 2013, and everything that FMI has property rights was opened. So you can freely get the data from this web page. So let's move on to the machine learning project that I made. So the title of my project work was predicting the errors in 2-meter temperature forecasts during wintertime in Finland. So during wintertime in Finland, there is no diurnal variation in the temperature. The sun is not warming us at all because we are so far north. There are fast and large local variations in temperature. They are very common, and they are strongly related to the low-level cloudiness and the wind speeds. So here is a couple of images that I try to give you some idea of the problem. So the upper image is an atmospheric sounding, actually just zoomed picture of the lower part of the atmospheric sounding. So the y-axis is the height, but it's now here in hectopascals, so it's pressure. And in here in the x-axis, we have the temperature. And the blue curve here is the most interesting one. It's the actual observation of the atmospheric sounding from northern Finland. And the gray curves here behind the blue curve, they are model modeled atmospheric sounding. And what happens here near surface is that we have a situation that we call inversion. So normally the temperature gets lower the higher we go in the atmosphere. But here near surface we have an inversion situation, so the temperature is actually rising when we go higher in the atmosphere. So this phenomena happens in very shallow layer near the surface. So these are very difficult for the model to get correctly. And these are very common in our cold climate. And this is a known problem, and you have to understand, and even though the model is really good that we are using, but these situations are very difficult for the model to catch. But they cause very large errors in our forecast. For example, in here we have a time series of observed temperature in dots, and then we have one model forecast here with solid line, and the temperatures drop almost to minus 30 degrees of Celsius, and the model is forecasting about minus 20 degrees. So it's totally missing the coldest temperatures in here. So I was especially interested to finding a method to correct these very large errors that we still have in our model forecasts. So the model, even though the 2 meters temperature is quite difficult for the model to forecast, but there are other parameters that the model that are better forecasted in the model. So we can, in the weather model, so we can use those parameters providing and then put them in a machine learning, use them in machine learning methods and see if we can improve the weather model performance with those. So that was the main idea in my project work. So a little summary that what I did in my work. So I wanted to test a decision tree and random forest machine learning methods to predict the forecast error in temperature. I decided to use the forecast error, so the forecasted temperature minus the observed temperature as the label variable for a predictant. Another option would have been to forecast or try to forecast the observation, use the observations as the variable, but I was just thinking very practically that if you use try to forecast the forecasting error, so then it's a lot easier to create if we would use this in production. So we should create this information. But yeah, that was just my decision. I also produced a multilinear regression model trying to represent the MOS that we are having, even though the MOS that we are having in operations is a bit more sophisticated, but at least to give an idea how linear method is working, since the decision tree is non-linear. And I compared the results of the random forest forecast and decision tree with the raw model output, of course, and with the MOS. And I used mean squared error to validate my model data. And I randomly split my data to 80% of the data as the training data and 20% as test data. And I didn't use the test data to any validation, so I totally left it out just to see the model performance. And I used k-folds cross-validation to estimate the model performance. And I also tested tuning the hyperparameters of the random forest model. So a little bit more about the data. So I used FMI's MOS database, which is a PostgreSQL database. We have there stored model produced forecasts for observation points. So here is an example of just one observation point. This is Helsinki-Kaisaniemi, quite well-known observation point in Helsinki. And if we have a model data, it's linearly interpolated from the grids to this point and stored to the database. And we have an archive of around 10 years in MOS database. And I fetched the temperature observations from FMI's server. So it's the same place that you can actually get the open data that we are providing. So altogether, I used 16 features from the weather model in my training, and the data set I combined the forecasts from 3 to 48-hour forecast because, well, normally you should train the model for each of these time steps individually, but since this was the winter time and there is no diurnal variation, so the error is not that much dependent of the time of the day. So I thought that combining these hours, I was able to get more data for my model. And I used data from 5 winters, from 2013 to 2018, and for 90 observation stations around Finland. And I produced just one model for all of these stations instead of training one model for each of the stations, which you actually should do because the climate is very different in southern and northern Finland. But once again, I wanted to use more data and just experiment, so I combined it all together. So the data set consists of around 600,000 rows of data, where each row represents one forecast made for one station location, and all the features are in columns. So in summary, my model has features from a weather prediction model, predicted parameters. There are 16 of those, and the label is temperature forecast error that I tried to model or forecast. Very quickly, short introduction to the decision tree or the random forest that I was using. So decision tree is a tree kind of structure, so it's like upside down tree. There is one example of a tree that I produced, and it can be used in regression or classification. The nice thing about it is that it's non-linear. What it actually does, it breaks down a data set into smaller and smaller subsets, while at the same time the tree is growing. And the final result is a tree with internal nodes where the splits are, and then the leaf nodes, which are representing the results in here. If we produce a very complex tree, then it tends to produce overfitting, and simpler trees can produce better forecasts. Decision trees are suffering from high variance, so very small changes in training data may cause large differences in the resulting decision tree. So to fix this problem, we can use random forest. So instead of just one decision tree, we can create multiple trees using just samples of the whole data set and just a subset of all available features in each split. And then we are averaging the resulting prediction. So the increased randomness that we create lowers the variance and improves the forecasts in general. So very shortly also about the k-fold cross-validation and the hyperparameter tuning. So instead of using just a single split in training and test data, the model performance can be more reliably estimated using cross-validation. So if here is all the data, so I did the split to training data and test data and left out the test data. But then for the validation data, you can further split with k-fold cross-validation. You can further split the trading data so that you always leave some part out from training and use that one as a validation data. And do it multiple times so you get better estimates of the test error then. Of course, it's computationally more expensive to do this one. The hyperparameters in the model are the kind of model parameters that the user has to define themselves. They are not directly learned within Estimator. But in Scikit-learn, there are a couple of ways how to do this one, and I also found from the internet a very nice example how to use this randomized search cross-validation that I actually implemented in my project work also. So let's switch to the Jupyter Notebook. Are there any questions now? I don't know if I have much time left anymore.
We have around 10 minutes. One question was, how do you check, or how do you measure the quality of data? You have mentioned it's important to have high quality data, but how do you verify the quality of data?
You mean the observations?
Yes.
Yeah, we have to, well, there are, there are so many ways to do that one. And that's not kind of my cup of tea, so to say, but you can do kind of body checks. So we have our own observation system, and luckily we have quite many of those. So that those are called sign-up stations, and we can compare then other observations to those. So if they differ a lot, so then we can assume that they are not correct. And also for some parameters, we can know quite easily if they are unphysical. But there are statistical ways to do it and so forth. But there are quite many ways to do it, and it's not always as easy as one would hope. But let's go to the Jupyter Notebook quickly. So here is a quick view to my data in here. And then I wanted to plot just a scatter plot of the observed and forecasted temperature from the weather model. So here we have from all these data points, I have the observed temperature here on x-axis, and y-axis is the forecasted temperature. So this is the raw model output. And we can see that when we go in colder temperatures, the model is over forecasting them almost all the time. So this is the error that I would like to fix with machine learning. So here I'm just splitting the data to the test and training data sets. And here is an example of all these 16 features that I used. So these are just different parameters that the model is producing. And the 2-meter temperature is one of them that's used in training. Then I plotted just heat map to see if there is a linear correlation between the features and between the temperature difference or the forecasting error that I wanted to forecast. But there is not much. It's this row in here. This is something that I kind of knew already, that there is not very big correlation between any of these features by themselves to this forecasting error. So then I tested just a simple one decision tree so that I didn't put any amount how large the tree can be, and then I put some limitation that it can have only 5 levels in the tree. And the results, the mean squared error here was for the cross-validation. When there wasn't any limitation, the MSE was 7.2, and the training error was 0, so it seems to be overfitting. But when I limited, so it was a simple decision tree, I achieved a slightly better result, so it was 5.9. And the weather model itself, the mean squared error was 7.7. So actually, even with these very simple decision trees, I was able to get a better result than the raw model itself.
Just one comment to the students.
Yes.
I want to see in the reports at least once these 2 numbers, training set error and test or validation set error. These 2 numbers must be determined and must be also discussed in the report. And as Leila pointed out excellently, so we see immediately here training set error 0. So we perfectly fit the training data, but the test or validation set error is much larger. So this means overfitting. How can we combat overfitting? For example, reducing the complexity of the hypothesis space. In this case, reduce the maximum depth of decision trees.
Yes, and the cross-validation can be done quite easily. So it's just this line in here. So you're defining how many folds you want to have in the cross-validation, and you can even define what kind of scoring rule you want to have. So I wanted to have the mean squared error. I don't know why it's the the negative value, but I just took absolute value of the and the mean value of the what it gave me out. I don't know why it was negative value, but nevertheless. So it could really nicely estimate the test error. So these numbers are quite close to each other. And then I tried to just use some very basic hyperparameters, almost the kind of the values that are there by default. I just then tried a random forest model, and I was able to get a lot better results. So now the cross-validation mean squared error was 3.5, and the test set was 3.3. So much better result than using just the decision tree. So with random forest, we are taking average over a large amount of decision trees, and in this default setting, I had 20 trees that I used. So then I calculated just a very simple linear model, multilinear model to represent the moss. And with that one, I was able to achieve mean squared error values for 6.1. So it's better than the raw model, which was 7.7, but still with random forest, we are able to achieve much better results. So I just plotted scatter plots. So this is once again the same that we saw already. So observed temperature and the raw model. And in the middle, we have the result of random forest. So looks much better. And on the right-hand side, we have the results for the moss. So moss is able to correct, in general, the coldest temperatures, but random forest is performing a lot better. So very good results. So quickly then about testing of the random forest performance with different hyperparameters. So I already said this is a really nice example how to do this one. So there are a couple of methods that you can do in scikit-learn. I used the random method. So you can either put many values there and then go through all the options. But instead of that, I put some values in here, and then this randomized search is using just the random sets or combinations, and you can define how many combination it goes through, and you can also put there the value, how many folds you want to have in your cross-validation in here. So first I just had to create it where this method is taking the samples from, and actually before that I printed out all the possible hyperparameters that you can tune in random forest regression. So there are quite many of those. I don't even know what all of those do. But I then followed the really good example that I said, and then tried to tune these parameters in here, and they are explained also here, but maybe we don't have time to go through all of them. But then the randomized search is taking, in my example, they are taking 100 samples and using k-fold cross-validation with 3 folds. And it took quite a lot of time. Even though I just took a subset of all my data, it took half an hour to go through all this hyperparameter tuning, even though I had parallel jobs calculating it. But in the end, I came up, or the system came up with these values, saying that, okay, these values gave the best model. And then I calculate the model with these best values that I estimated, and was able to even further a little bit improve the quality of my model. But now the training set mean squared error is 0. So I'm wondering if this is also indicating that there is overfitting in my model. So the results were that the weather model, the mean squared error was 7.7. With moss, the mean squared error is 6.2. With simple, or the best decision tree with 5 max depth, it was 6. And with random forest, I was able to achieve a lot of improvement. And with tuned random forest, I was even further able to slightly improve my default random forest model. So I think this was really nice project work, and I really enjoyed this one a lot. And what could or should be done in the future, if I would like to continue this work, I would need to have a longer data set, probably more significant weather parameters to use in the training. The location and the time of the day probably should be taken into account. And I should learn more about hyperparameter tuning. So yeah, I think we only went like 2 minutes over time. So I think
no
I had
worries,
to
Leila.
hurry a bit at the end.
I took too much time in the beginning. Thanks a lot for your excellent presentation. Really interesting and a great demonstration of good use of machine learning. Are there any questions? There's one question. How well did the number of features used in your data affect the quality of the prediction? So did you try out using different number of features or only subsets of features?
Well, yeah, well, it kind of does evaluate how much you use in the hyperparameter. It was using also these two options, but not much actually. I also used this one in the default one. So I don't know, maybe I could, well, probably some of the features are insignificant, so I could leave them out. I didn't actually check which ones were the most important ones. I know there are a couple of ways to do it in the
okay, and as you already indicated in the final result that you got from this hyperparameter tuning, the training error was 0, which indicates overfitting. So did you use this these numbers, training set error and tested error for coming up with the suggestion for what could or should be done?
Well, what could be done is now when I got some rough estimates of the hyperparameter values, I could further this experiment by another option was what was available, that you actually go through all the options of the hyperparameter tuning, but it would have taken even more time.
Yeah, but my question was mainly how did you come up with this suggestion for further improvement? Is this based on your experience, or was this because you said it seems it's overfitting, so what can I do to reduce the overfitting? For example,
yeah, I was wondering if it is overfitting. I don't know the answer, to be honest.
It seems so. If the training error is 0, so it perfectly fits the training data, this seems overfitting. So how can we reduce overfitting? Anybody else having a suggestion? How can we reduce overfitting? There are at least two options. First is collect more data. As Leila pointed out, longer data set, more significant. Well, to increase the number of features might not be helping against the overfitting. Might actually increase overfitting, but reduce the number of features. So trying to get somehow the most relevant features, but as you pointed out, Leila, it seems that all features have some influence.
Well, the lucky thing is that since I'm a weather forecaster, I kind of know what are the most significant weather features, but then there might be some. Well, actually, I know that there are features that the model is forecasting, but we just haven't been storing them.
Yes.
So one thing about reloading of the data for the MOS database is we have been now ordering more of these significant variables that we know that we would like to have, but we just don't have that information yet, so to say.
Yes, another comment from the students. Yes, to combat overfitting, we can do regularization. So and this is maybe one of the hyperparameters, I guess. There were so many hyperparameters. I think one of them is the strength of regularization. See it yet. Max leaf. Security. No, I don't see it here. But I think one can combine decision trees with regularization in scikit-learn. If not, then this is something one can do also by hand. It's a bit more work. Yes. But it's nice to see that that you clearly were able to improve the predictions using the post processing.
Yes, that's the nice thing about these methods, that we have been reporting these problems to the model developers for quite a long time already. Yes. But since it's a global model and they have suggested some improvements, but then when they are testing the global model, those improvements caused worse or poorer forecasts for the tropics. So they cannot implement those. Those so easily. They cannot do modifications to the global models that easily. Instead, if you want to just provide better forecasts for Finland, we can run some kind of machine learning model quite easily on top of the weather model.
So there's one, I would say the last question. You mentioned that you divided the data points into 80-20%. How did this strategy affect your solution? And how did you come up with this strategy? Was there a specific reason for 80-20 split?
No, I think it was just some recommendation. I did a lot of Googling, so I just found it somewhere and used that one. So it was just 20% I left out for the testing. So it was kind of data that I didn't use at all in the training or the hyperparameter tuning at all.
Okay. Thanks a lot, Leila, again, for this great talk. And you are also completing now the deep learning with Python course.
Yes, I am.
So maybe you could try out this problem, but with deep nets now.
Well, I was thinking about trying actually ensemble calibration, so something a bit different.
Okay. Okay, thanks again. And
yeah, thanks for having me. Okay.
Thanks a lot. And have a nice evening.
Yeah, you too.
Bye.
Bye.